We're next going to look at epoxides. What is an epoxide? An epoxide is a three-membered ring with an oxygen. Of course, we would have other things coming off. I'm not going to show what's out here. These could be hydrogens or other groups or whatever, but an epoxide is a three-membered ring with an oxygen in it. One oxygen. That's an epoxide. Let's look at how to make epoxides, and then we're going to look at how they're used. Epoxides, so this is a cyclic ether. We are looking at ethers right now. This is just a cyclic ether. Epoxides are made from alkenes. You can use any alkene. I'll just show this one. This one's a mono-substituted alkene, but you can use a di-substituted or unsubstituted or tri-substituted, tetra-substituted, doesn't matter. Any alkene. And we're going to react this with a peroxy acid. This is a peroxy acid. It's a cross between a carboxylic acid and a peroxide. We know a peroxide is an oxygen-oxygen bond is a peroxide. But you can see it also looks like a carboxylic acid. If this was an OH group here, it would be a carboxylic acid. But we have the O bond there first, so that's a peroxide. So we cross it, it's a peroxy acid. If you take any alkene with a peroxy acid, we will make the epoxide, and then as a byproduct we get a carboxylic acid as a byproduct. So the peroxy acid turns into a carboxylic acid. We lose that one oxygen, it goes to make the epoxide. This reaction to make an epoxide, it's called an epoxidation. It's not important, but epoxidation makes an epoxide. And most people will call this a sharpless, they now will call it a sharpless epoxidation because of the guy that first started doing all these epoxides. His name was Barry Sharpless. He won a Nobel Prize for his work just a few years ago. I think it was about in 2005, 2006, somewhere along in there. So it's not been too long ago. He won a Nobel Prize for his epoxidation reactions. I had an opportunity to go work with him, and I chose wrong. I turned him down. So after I finished my PhD, most people will do what's called a postdoc. It's just it's a position where you can just learn more chemistry, more research. And so I had several postdoc offers, and I wound up working for Joel Miller at University of Utah. He worked on organic magnetism, and I thought he had the best chance of winning a Nobel Prize, so I went to work for him. Turns out Barry Sharpless wound up winning a Nobel Prize, so I chose wrong. And one of the others that I had was Dennis Curran. He was at University of Pittsburgh, and Pittsburgh. I know it's a decent school, but I don't want to go to Pittsburgh. Well, 6 months after I turned him down, he moved to MIT. I'm like, dang it, I could have been at MIT. So I chose wrong all the way around. But anyway, if I'd went to work for Sharpless or wound up with Dennis Curran at MIT, I wouldn't be here at Mississippi College. I'd be at some big school and be a totally different person. So it all worked out. I'm happy here. Anyway, so most people will now refer to these as the Sharpless epoxidation since he's won a Nobel Prize. Most textbooks are starting to put that in. Before, it was just epoxidation. Now, I'm going to show you a mechanism for it. I will not ask this mechanism on the exam. This is a complicated mechanism. But I will show it to you. Let me redraw my peroxy acid over here, and I'm going to kind of curl it up a little bit. That's my peroxy acid. Same thing, just curled up. And I'm going to put the alkene down here. Now, like I said, this is complicated. We got arrows going everywhere. We get a lone pair from the OH oxygen. That's going to attack the alkene. Attacks the I'm going to use the green one. The green one's working better. We get electrons to come out of the double bond back to that oxygen. The oxygen-oxygen bond's very weak, so that kicks these electrons in to form a double bond between the oxygen and the carbon. That kicks these out to come in and grab the hydrogen, and then these electrons go back onto that oxygen. If you followed all that. Maybe I'll put little numbers beside them so you can kind of see. Of course, all this happens at the same time. It's not step 1, 2, and 3, but you know they follow each other. Put some little numbers there so you can kind of see how they work. But like I said, I will not ask that mechanism on the test. It's very complicated to get all of those going everywhere. But that gives us the epoxide that I had up there before and the carboxylic acid. So let's look at some examples. Let's do a cyclic alkene. The most commonly, any peroxy acid will work. The most common peroxy acid is MCPBA. That's the most commonly used one. It works extremely well, so that's what most everybody uses. Let's take a look at MCPBA. This is what it looks like. So it is a peroxy acid. There's the peroxy acid portion. And then in the Then on the ring there's a chlorine. This is the name of this is M-chloro or metachloro. metachloroperoxybenzoic acid. So that's how they get the MCPBA. It's MCPBA. So this is our MCPBA. That one works, like I said, works extremely well. That's the one everybody uses. So that's the one I'm going to use. I'm not going to give you any others. There's some other peroxy acids that work just as well, but everybody uses MCPBA, so that's what I'm going to stick with. The MCPBA will make an epoxide right there where the alkene is. There's our product. Those two carbons of the double bond become the epoxide ring. We're adding the oxygen in. Let's do another one. Now, we don't touch the phenyl ring. Phenyl ring's too stable. I'm not going to touch those double bonds, but my alkene out here, that's outside the phenyl ring, that's what's going to react and make the epoxide. So there's our epoxide ring. Questions? So we're going to begin on chapter 12. Chapter 12 is all about carbonyl compounds. A lot of Organic 2 is about carbonyl compounds. And we are going to begin by looking at making alcohols from carbonyls. Let's just review just a moment. Carbonyl, of course, is a C double bond O. That is a carbonyl group. We can have different things on each side, but this is our carbonyl group. The carbonyl group is somewhat, well, it is special. It's got resonance. We can draw resonance where we take the electrons up onto the oxygen. There was 2 lone pairs on the oxygen. Now there's 3 lone pairs. Of course, your curved arrows get your charge. Initial tail always becomes more positive by a charge. So plus charge on the carbon. Final head becomes more negative by a charge. There's a full negative charge on the oxygen. Of course, our real structure is a hybrid of the resonance structures. I'll draw a hybrid. So we got partial negative on the oxygen, partial positive on the carbon. Just a combination of our resonance structures. Now, as we go throughout this chapter, and even future chapters, we're going to be looking at different carbonyl compounds. We have aldehydes, ketones, esters, carboxylic acids, or amides. We have all these esters. We have all these different functional groups that contain a carbonyl. So we will be studying all of those. And we'll also be studying different nucleophiles reacting with carbonyls. So when a nucleophile reacts with a carbonyl, let me just redraw a carbonyl down here. Because there's the partial positive charge on the carbonyl carbon, our nucleophile is going to be attracted to that carbonyl carbon. Now, to avoid breaking the octet rule, we'll kick electrons up on the oxygen. You learn that one little mechanism right there, and you've learned half of Organic 2. You will see that over and over and over again. Nucleophile attacking the carbonyl carbon, we kick the electrons up on the oxygen. like I said, we're going to study different carbonyls and we're going to study different nucleophiles, but they all work the same to start with. There are some differences further on down the line, but the initial reaction is the same, the initial step of our mechanism. So learn that one mechanism and you have learned, like I said, half of organic 2 right there. Now, to be successful in this class, you need to learn mechanisms. Learn how these reactions take place. Learn the mechanism, and you learn one mechanism, you've instantly learned thousands and thousands and thousands of reactions. You try to memorize them all, you're going to get in trouble really quick. You can't memorize all of these reactions. Our first reaction that we're going to look at is alcohols from carbonyl compounds. So let's take a look at that. We're going to be looking at reduction of carbonyls. Let's look at some different carbonyls that we can reduce. We're going to look at reduction of a carboxylic acid, and I'll just go generic here. We can reduce a carboxylic acid. Now I will talk about here in a moment what kind of reagents we need to do the reduction. I'm just going to say reduction right now, and we'll talk about the reagents that are necessary to reduce a carboxylic acid. But a carboxylic acid we can reduce to a primary alcohol. Now there's no reason to memorize that, because if you learn our mechanisms, then you can figure it out. There's no reason to memorize that. Now a reduction, if you recall from Organic 1, oxidation and reduction is different for organic chemistry than it was in general chemistry. General chemistry, we're talking about electrons. In organic, we're talking about hydrogens for a reduction. So, or also talking about oxygen as well. So let's just talk about what a reduction is. We'll review real quick. For an organic chemist, reduction of an organic compound corresponds to increasing the hydrogen content or decreasing the oxygen content, or both. And oxidation is just the opposite of that. I'm not going to write it up there. Oxidation would be just the opposite. Oxidation would be decreasing the hydrogen content or increasing the oxygen content, or both. And we will be looking at some oxidations later in this chapter. But right now we're focusing on reduction, and the oxidation will be just the opposite here of the reduction. So you can see the carboxylic acid, we have both increased the hydrogen content. You can see there's more hydrogens here. And we have decreased the oxygen content. So we've done both here for the carboxylic acid on this reduction. We're going to look at reduction of some other carbonyls. So let me go ahead and put those up. And then, like I said, we'll go back and talk about the reagents necessary to do the reduction. We can reduce an ester. We can do the reduction of an ester. We also, for the ester, we get a primary alcohol when it's reduced. We're going to be looking at the reduction of an aldehyde. And if we reduce an aldehyde, we get a primary alcohol. And finally, we'll look at the reduction of a ketone. If we reduce a ketone, we get a secondary alcohol. So all the others gave primary, but the ketone gives a secondary alcohol. Okay, so you can see with the reduction, we've increased the hydrogen content or decreased the oxygen content or both in some of these. Now let's talk about the reagents necessary to do the reduction. We can reduce, we did some reductions in organic 1. Anybody remember a reduction we did in organic 1? What was a reduction we did? Anybody remember one? We did a reduction, let me remind you a little bit. We did a reduction of alkenes and alkynes to an alkene. So what did we do?
We did hydrogen with
hydrogenation. We did hydrogen with some catalyst. Well, we can do hydrogenation with some of these. So that's the first one we're going to look at. So let's look at reduction by hydrogenation. Now the hydrogenation only works for aldehydes and ketones. It does not work for the other carbonyl compounds. So here is, I'm going to do an aldehyde. And we're going to add in hydrogen gas. And we need a catalyst. You can use platinum, palladium, nickel. That's what we learned in organic 1. I'm going to add one more in here. You can also use ruthenium. And then these are usually done under high pressure as well. This will reduce the aldehyde to a primary alcohol. Let's look at how it works. So our catalyst, I'll choose palladium. That's the most commonly used one. The catalyst coordinates with the double bond and the hydrogen molecule. It weakens those bonds and brings everything together. Our mechanism is we're going to take a pair of electrons out of the double bond to come out and grab one of those hydrogens. And then the electrons in the hydrogen-hydrogen bond, they're going to go with that hydrogen and go to the other end of the double bond. So one hydrogen is going to the oxygen, one is going to the carbonyl carbon. And that gives us our product. So the same thing would happen with a ketone. So we can reduce aldehydes and ketones by hydrogenation. Now, with this reduction with only aldehydes and ketones working, that tells us a little bit about different carbonyls. There is a difference between these different carbonyl compounds. Some of them are easier to reduce. Apparently, aldehydes and ketones are the easiest to reduce because they work here, but the carboxylic acid and ester doesn't. So they must be more difficult. They're not working with these conditions. So let's talk about the ease of reduction. The carboxylic acid is the most difficult to reduce. A little bit easier, more reactive, is the ester, but it is also very difficult to reduce. Now, easier than that is ketones. And the easiest carbonyl to reduce is the aldehyde. Okay, so that's our order here for the ease of reduction. The aldehyde is the easiest to reduce. Then the ketone, ester, and the carboxylic acid is the most difficult. Now, some of this makes sense. Let's think about a little bit why some of these are harder, some of them are easier. The carboxylic acid and the ester, they are the two most difficult to reduce. And let's look for a reason. What do these have that the aldehyde and the ketone doesn't have? Why are these more difficult to reduce?
Induction.
Yeah, they have some induction, but induction effects are always very, very small. Like when we looked in induction effects affecting acidity, now we changed it 1 or 2 pK units.
Delocalization of the electron.
Yes, in other words, resonance. They have additional resonance structures. So with these two, we have the extra oxygen that is doing resonance with the carbonyl. So the reason these are difficult to reduce is because of resonance. Additional resonance. Let me just draw one of these up here. I'll do the carboxylic acid. Let's look at that carboxylic acid. Now, any carbonyl has resonance. I can take the electrons up onto the oxygen. So all carbonyls have some resonance. By the way, it's not a huge amount. Let me give you an example. Here is acetone. And we mentioned that you can take the electrons onto the carbonyl. So this has resonance, but it's not a huge amount. Let me give you the percentages on acetone. I know those off the top of my head. Only 10% exist in this form, and 90% exist in this form. So, that resonance is not that important because we're separating charge and all of that. So it's not that important of a resonance structure. So we still have that here with carboxylic acid and ester. I still have the carbonyl resonance that I can do. But we have another oxygen that can do resonance. These electrons can kick in to the carbonyl. So I have an additional resonance structure that I can draw for these. Always keep track of your charges. Initial tail becomes more positive by charge, where we started. Final head becomes more negative by charge, so that oxygen has a full negative. So both of these have this additional resonance structure in addition to the regular carbonyl resonance. So these have more resonance structures. More resonance means you're more stable. More stable means you're less reactive. So these are less reactive. They don't want to reduce. They're happy where they are. They're doing all this resonance. All the electrons are delocalized. All the electrons are moving around. So it's hard for anything to react with them because they're moving so much. If they stay in one spot, then we can react with them. So that electron delocalization is stabilizing those structures. So they don't want to react. Okay. So hydrogenation can do ketones and aldehydes, but it cannot do esters or carboxylic acids. Now, hydrogenation is all good and fine, but it's difficult to do a hydrogenation. You're dealing with a gas. You're dealing with hydrogen gas. It's difficult to work with a gas. We have to buy a cylinder of it and then hook up some hoses and just bubble some hydrogen through the solution. Plus, hydrogen gas is very flammable. That's what blew up the Hindenburg. That was hydrogen gas they were using to float the Hindenburg, and kaboom. So we don't like to have to use hydrogen gas. Is there some other reagents that we can use to do the reduction? And the answer, of course, is yes, and that's what we're going to look at next. So let's look at some other reducing reagents. This is still on section 3. We're going to look at two different ones, two more. The first one I'm going to put up is sodium borohydride. And the other one I'm going to put up is lithium aluminum hydride. Let me draw these structures out and let's examine these a little bit. The borohydride, we've got 4 hydrogen atoms around the boron. Sodium balances charge out. We don't care about the metals. We're organic chemists. We don't care about the metals. So the sodium is balancing the charge out with that. There's a plus charge on the sodium. It's out there floating out there somewhere, but we don't care about the sodium. If the borohydride loses a hydride, hydride's an H minus. If it loses an H minus, then the boron can become neutral. So this likes to transfer an H minus. Lithium aluminum hydride looks very similar. Negative charge on the aluminum. Lithium's balancing the charge out. We don't care about the metal. There's a plus charge on the lithium. It's floating out there. We don't care about that. It's the aluminum hydride that we're caring about. It would also like to transfer a hydride, an H minus. If it can lose an H minus, a hydride, then the aluminum can become neutral. And so it likes to do that. Of these two, lithium aluminum hydride is the most reactive. Sodium borohydride is not quite as reactive. We're going to see here in our future sections here, sodium borohydride being less reactive, it will reduce aldehydes and ketones only. lithium aluminum hydride, being much more reactive, reduces all carbonyls. So make certain you learn the differences there. Lithium aluminum hydride, much more reactive, it'll reduce all carbonyls. Lithium aluminum hydride has an abbreviation that's often used, so let me write that down. Instead of writing out the words or the formula, we often just call it LAH. LAH is lithium aluminum hydride, is what that stands for. Now, the difference between the two, the reason lithium aluminum hydride is more reactive, it's the size of our atoms here. The aluminum is a much larger atom. The boron is much smaller. So boron being smaller is holding the electrons closer to the nucleus. It makes the hydride more difficult to leave. Because we know the nucleus of an atom is positively charged, so the closer we can get everything to the nucleus, the more it wants to hang on to it. So it's hanging on to that negative charge a little tighter. Aluminum, big, large atom, it doesn't even know those hydrides are out there. It's the large. So it gives up a hydride much easier. Now, lithium aluminum hydride, you have to be careful with it. It is extremely reactive, and we have to protect it from water. It will react very violently with water. Not only is it a good reducing reagent, it is an extremely strong base because it likes to transfer in hydride, and we know a hydride is a strong base. So this reacts violently with water. Or any other acidic hydrogen. I know this from personal experience. You get it in contact with an acidic hydrogen and you will have a massive fire on your hands that you can't put out with any fire extinguisher. And like I said, I know this from personal experience. I will share it with you here. So when I was a postdoc at the University of Utah, we had in the lab, this stuff will go bad over time. It will react with the moisture in the air over time. And so a can of this will go bad over time. And so we had in the lab, we had about 20 cans of lithium aluminum hydride. Because we know it's going to go bad over time, so every year we normally just order a brand new can because we didn't trust the old stuff. And so the professor that I was working with there said, asked me as the postdoc to destroy all of the old lithium aluminum hydride that we had. So what you do to destroy it, you add in a weak acid to destroy it. So I was using isopropyl alcohol to destroy it. And you want to go very slow. You add it in very slow. In lab, we often will do it drop-wise. So that's what I was doing. I was going drop-wise. And I was being very careful. But I had 20 cans of this to destroy. And whenever we get a can, we always put the date so we know which one is the newest can, and that's the good stuff. So it had dates on all of these, and I started with the newest one, and I was being very careful. And about can number 19 of destroying, I was back to 1969 was the date on the can. And of course I'm adding the isopropyl alcohol very slowly, and it'll bubble up and fizz and everything because you get hydrogen gas coming off when it reacts. But on this can, as I'm adding the alcohol, nothing fizzed, no bubbles, no nothing. It was dead. It was not reactive at all. It was no good, completely no good. Nothing was happening. Now, I had one more can to go. And that can said 1967. So if my logic was, I'm getting very tired of doing this. If the 1969 can was no good, 1967 can also must be no good. And so I was getting so tired going dropwise, one drop at a time. So what did I do? I added it way too fast. I didn't go dropwise. I just poured a bunch in, and it was still good. Kawoom! Huge fire. We hit it with a fire extinguisher, wouldn't touch it. I finally got the fire out by smothering it out. Luckily, I was in an Erlenmeyer flask, and so all I had to eventually figured out, just put a watch glass on top, and it smothered it out. But the fire extinguisher wouldn't touch it. Okay, so keep water away from that reagent, even on your exams. Don't put water in there with it. I will count off on you if you've got water in there with the lithium aluminum hydride. So what you have to do is, we often need a proton source like water. You have to add that in a separate step. And I'll show you that here when we look at some examples. So let's look at some examples of these two. And we'll look at our mechanism. So we'll do the sodium borohydride first. We'll do sodium borohydride. You will do the reaction in water or an alcohol. Any alcohol will work. We need a proton source. So those are providing us a proton source. Now, I can have those in with the sodium borohydride at the same time, because sodium borohydride is not as reactive. It's not going to explode on me like lithium aluminum hydride would. So we can have those in there together. Our product is we reduce the carbonyl to an alcohol. Now let's look at the mechanism. Let's see how we get from the starting material to that product. But first, we're about halfway through the class. So let's take about a 5-minute break.